Hey everybody. As I said in class, unfortunately I had another set of technical difficulties where my recording of this lecture didn't record. So I'm re-recording in my office. So this is the lecture from February 17th. It was a Tuesday. Just a heads up, add drop date is coming up soon, and I am doing everything in my power to get you exam 1 grades posted to Canvas before that add drop deadline. Okay, at the start of class, I did a small little bit of lecture about Euler's method. And the reason that I did this is because you're being asked to implement Euler's method in the project module 1 directions. So on your project, you're asked to solve a problem analytically, which is where you actually do the integral, where you add 1 to the exponent of a polynomial and divide by that new larger exponent. You follow all the integration rules that you learned how to do in your original calculus classes. So that's called analytical integration. Now, sometimes that works great. And other times there are functions that we actually cannot analytically integrate. And so that's when we tend to use numerical methods. And numerical methods are those that are basically made for a computer to do. It's basically an algorithm that approximates our analytical solution. Okay? So we're going to learn about that today. And one of those numerical integration methods is called Euler's method, and we'll look at that. Okay? So why are we doing this? Well, when you have acceleration in a problem, like you do for maybe projectile motion, where we know that the only force acting on this object is in the negative y direction, so gravity's pointing down, that's the only force. You want to be able to integrate that acceleration to find velocity. Okay, so the key word being you need to integrate. And then if you have velocity and you want to figure out what your position is going to be over time, you have to integrate again. So keyword being we have to integrate. Okay, and the way that I want you to start thinking about this integration is that it allows you to predict the future, which is one of the reasons that I love the content in this class so much, is that it allows us to predict the future. Okay, so if we think more closely about projectile motion, when we know the acceleration as a function of time and some initial conditions, we're able to leverage that information that's given just about what's happening at the very first time step before, like right as it's being projected into motion. We can use that initial information to predict the position of this thing at all other points in time, right? So if we have this kind of canonical cannonball being shot out of a cannon picture here, as long as I know V0 and P0, so the position and the velocity only at the first time step, I can predict this parabolic path in purple for the rest of the time steps throughout the flight. And that's really, really cool. And the way that I do that is by integrating. Okay, so far in this class, we've had to integrate things that have been pretty simple, right? Like we've done a lot of polynomial integration. So maybe our acceleration is some constant value, and so we can integrate that constant, and it just ends up being multiplied by t and evaluated from at the bounds, right? So those are things that are easy to integrate by hand, but there are some expressions that you actually cannot integrate analytically. If I sat you down and said, tell me the integral of sine x over x, no matter how many integration rules you know, you would not be able to solve for the integral of that function. Same with e to the minus x squared. Okay, so even though an analytical solution is not available, we sometimes aim to approximate the true integral, which would be our analytical solution. In fact, another way that some people say the analytical solution is to call it the exact solution. So one way that we approximate the exact solution is by using numerical integration. So the important thing to note here is that numerical integration is and always will be an approximation, meaning that there will be some error between what you get from your numerical integration versus what you would have gotten if you were able to do an analytical integral. Okay, but there are some knobs that we can turn to make that error very, very small, and we'll talk about that today. Okay, so the basis of the way that we build up this idea of numerical integration is going back to this very visual reminder of what an integral is. So sometimes in calculus, you'll learn that the integral is the area under the curve, right? So if we have some function here, maybe we'll call it g. Maybe this is g of t. We'll call this g. And maybe we want to know the integral of this function from t0 to t final. Well, we know from our early calculus classes that this is the area underneath this curve down to the x-axis. And once we learned that it was the area under the curve, then our calculus teachers taught us about little teeny tiny little area elements. And they said, we can do this integral by adding up these teeny tiny little slices. And these teeny tiny little slices, the height of that slice is equal to the function value at that at that time t. And then the width of this slice is a dt, an infinitesimally small width dt. And that's how we built our integral. We said that if we integrate the height of these things times our width dt, so we add up a bunch of areas of little tiny elements, area of a tiny rectangle. Whoops. And then we add that up from t0 to t final. That's our integral. That's the area under the curve. Okay. Well, what we're going to do today is we're going to kind of loosen this definition a little bit. And by loosen, I mean that we say, okay, it would be fantastic if we could do the integral where we have an infinitesimally small delta t. But for whatever reason, we're not able to do that integral. So what if instead we chose slightly larger rectangles, where the width of this rectangle is not dt, it's not infinitesimally small. Instead, it has some width, maybe delta t, it's some change in time, so maybe this is t1, t2, t3, and maybe t1 is equal to t0 plus delta t. So it's not infinitesimally small, but we can kind of convince ourselves that this is still a pretty good approximation, right? There's a little bit of error between what our rectangles will say is the area versus what our integral might say is the area, but it's an approximation, right? There's not all that much difference. Okay, so what we're gonna say is the integral from t0 to t final of g of t dt is roughly equal to the sum of all these rectangles. And they're not infinitesimally small anymore. Okay, so that's the job of our numerical integration. Now, I've been kind of hand wavy about exactly how we're defining these rectangles, okay? And there are actually a lot of different ways that you could define these little rectangles or these little elements. And one of them that we're going to cover today is Euler's method. It's one of the simpler ways of defining these elements, okay? So we're going to learn Euler's method. That's what you're being asked to do in the project. However, you should know that there are lots of other methods, and they have different pros and cons to them, different levels of accuracy. And in fact, if you are familiar with MATLAB and you use ODE 45, ODE 45 is actually a numerical integration method. It works based on a method related to the Runge-Kutta method. It's a different method that's a bit more complex than what we're going to learn today, but And it's kind of interesting background information if you want to know what's under the hood in MATLAB. Okay, so let's do Euler's method today. And let's say we're given some df dt. So what's an example of a variable that is expressed as a derivative in this class? Well, maybe this is acceleration. Maybe we know the acceleration of our object is some function of time, okay? But we want to know, what is the integral of that? What is the integral of something that's been derived? Well, it's the base function as it is. So if we're given acceleration, maybe we're wanting to find velocity, okay? So we want to know f of t. We're given df dt. So we're given this blue line, but we want to know, what is that the derivative of? Okay, so usually we will know something about the initial conditions of our function f of t, right? So let's say we're doing projectile motion, we're given acceleration, but we also usually know the initial condition of the velocity, right? We usually know what velocity it's being fired off at and the angle that it makes with the horizontal, okay? So usually we know f of t0. That's our initial condition. Okay, so the way we're going to define this element is we're going to say, okay, the height of this element on the left side is going to be the initial condition. And then I'm going to make the top of this element sloped. And I'm going to say that this element has the same slope as my function f of t does at the point t0. Well, how do we find the slope of f of t at t0? Oh, we just need to plug in t0 into df dt. That's this given function, this blue function. So what is this value here? This is g of t0, which is the slope of f at t0. Okay, so that value becomes maybe the slope of this element. Maybe it's like this. Whoops. So we're going to approximate that our function has a constant slope between t0 and t1, with this width being delta t. And so the right-hand side, the height of the right-hand side, depends on delta t and my g of t0. Okay, so here's the equation that we use to find f of t1 if we are given f of t0. We say that f of t1, which in and of itself is t0 plus delta t, is equal to f of t0 plus a step along that slope where g of t is the slope of f of t, right? Because g of t is the derivative function that we are given in the problem. And then we do this repeatedly. We say, okay, now what is the slope? What is the slope of f of t at t1? I go from my prior position of my last element and I apply that new slope until I get to t2. And I say that f of t2, which is equal to t1 plus delta t, equals f of t1 plus delta t, oh, sorry, this is t0, g of t1. And I can do this iteratively, over and over and over again. Oh, that looks like it has a higher slope, so I should pretend that this has a higher slope. Something like this. Okay, so we say f of t3, which is equal to t2 plus delta t, equals f of t2 plus delta t g of, whoops, too many parentheses, g t2. All right? So recognize that the output of this first line becomes what gets plugged in here on the next line. Similarly, the output of this second line goes here for the third line. Okay, so this is a repetitive, iterative process. All right, and one of the most important things to know is that as delta, we get to choose delta t, right? But delta t sets how coarse our approximation is. But as delta t gets smaller and smaller, the closer the numerical approximation of the integral will get to the true or exact analytical solution. Okay, so if we want to do a very, very similar process over and over and over and over again, that should trigger in your mind that this would be a good program for MATLAB that we might put within, for instance, a for loop. It's because a loop is what does the same thing over and over and over and over again. Okay, so for your project, you'll basically need to interpret these equations and turn them into a for loop in MATLAB. Okay, if this resonated with you, great. If it didn't, there is a different version of an explanation of Euler's method that I have posted on Canvas. So there's a separate video. It is linked on Canvas. If this is totally confusing to you, maybe go check out that video next. Okay, we're going to go on to our regularly scheduled material. So today we're moving from the very last section that we did before exam 1, which was relating 2 points on the same rigid body. So that's depicted here. From our last class before the exam, we learned equations for relating 2 points that are fixed on the same rigid body. Okay? Now today, we are learning a little bit more complicated of a process where we're going to relate the movement of 2 points that are not on the same rigid body, but their movements are somewhat related to each other. So they're not necessarily on the same rigid body, but they are related in some way. And it'll become more obvious when we look at some examples. Okay? However, let's talk about a silly scenario. And I'm going to use this scenario to help introduce all of the different reference frames that we're going to talk about today. Okay? So my husband likes to play disc golf or frisbee golf. And I thought it was a great example of one way that you might think of these frames. So essentially, we're going to look at 3 different objects. And we're going to play around with reference frames and velocities and accelerations of these 3 objects. So the first object is your disc golfer. So this is a person. And for the most part, the disc golfer stays completely still, at least once they've already thrown the disc. And so let's pretend we have a disc golfer standing right here. They've already thrown, and they're just watching as their disc flies through the air. So they stay completely still. And we're going to assign a reference frame to our disc golfer, okay? Our disc golfer is going to represent the origin of what we'll call our big X, big Y, big Z frame, okay? Notice that I have these little serifs on here, so little extra doohickeys on my letters, and I've written them bold. I'm trying to make sure that I'm indicating that these are capital letters, okay? The capital letter XYZ frame is the one that stays put, it's fixed to the earth, and it never ever moves. Okay? So that's our first frame. The next thing we're going to worry about is the frisbee. Now this frisbee is both spinning and translating through space, right? It's rotating and it's moving through space. And we're going to put a reference frame fixed to the Frisbee. We're going to put another frame that goes like this. And this red frame is going to move with the Frisbee. It's fixed to the Frisbee. So this little red frame is going to translate and rotate exactly the same as the Frisbee. All right. So notice that I've written these little x, little y, little z. I've written them kind of curly and little, and that's to indicate that these are lowercase letters. Okay. And the very last thing we're going to worry about is basically an ant who is going for a joyride on top of the Frisbee. Okay, so we've got this little ant who's going for a joyride. They're on the Frisbee, and they're moving relative to the Frisbee. So this ant is crawling around the Frisbee. And for whatever reason, maybe we consider that this is like an OCD ant who has a lot on their mind, and they have a very repetitive, interesting motion, which is they're moving back and forth along the Frisbee only in the X direction of the Frisbee. So only along this little red X direction if we were to look at this Frisbee from above. Okay, so the ant is just moving forward and backward from the origin and back out to the edge, to the origin, back out into the edge. Okay, so this is important because the movement of the ant is basically very, very simple relative to the disk. So relative to the disk, you're only moving in the X direction, forward and backwards. However, we know when we start to worry about forces, that we need to analyze the motion of the ant from an inertial reference frame, not from this reference frame that's rotating and moving with the Frisbee. Okay, so what we really need to know is how is this ant moving as perceived by the disc golfer? And that motion is going to be incredibly complicated because this disc is spinning and rotating, it's rotating and translating, and the ant is moving along the surface. So we'll draw in a second roughly what that is going to look like. But let's add a few notes here, okay? So I'm going to add some notes to say that big X, big Y, big Z stays stuck to the page, and it doesn't move. Little x, little y, little z is stuck to the disk, meaning that it rotates and translates with the disk. Okay, and lastly, the ant moves forward and backwards along the pure X direction of the disk. Okay. Another thing I want to add is that each of these frames has its own associated unit vector directions. Okay, so this big X, big Y, big Z frame, I'm going to give it the unit vector big I hat, big J hat, big K hat. Okay, and this little XYZ frame, I'll say, I'm going to say this one goes with little I, little J, little K hat. Okay? Note, the ant does not get its own reference frame. The Frisbee gets the reference frame, not the ant. Okay? So we added the unit vector directions. And then the last thing I want to do is talk about different points in space. So let's see. We're going to call the origin of the little xyz frame, we're going to call that point A. And we're going to call the ant point B. Okay, that'll be important later, so just hold on to that fact. Okay, so let's go back to talking about who sees what in terms of the ant's movement. So if you are the disc golfer and you're trying to track how this ant is moving through space, well, we're going to pretend that the Frisbee is just moving in a completely flat path. It's just moving along this plane, this XY plane. Okay, so the Frisbee is moving straight across, and the Frisbee is rotating, and the ant is getting closer and farther away from that center of rotation. Okay, so when it's out towards the edge of the disc, it's going to rotate in big circles. As it gets into the center, it's going to get in smaller circles, and then he's going to turn around. He's going to start going in bigger circles again, and smaller and bigger, okay? So you can see that this is a wild and crazy path to be taking through space, which is not perfectly in any one given coordinate direction, right? However, if you shrink down to the size of an ant, and I place you on the red little XYZ frame, so you're also stuck to the Frisbee. Relative to the Frisbee, you just see the ant moving back and forth along the x-axis, which is a very, very simple movement. Okay? And it's this fact that this is a very, very simple movement relative to the moving frame that we're going to exploit with today's equations. Okay? So let's talk a little bit about problem solving with this type of problem. So for each problem, you will need to choose an appropriate location for the origin and an orientation of the axes for both the fixed XYZ and the moving little xyz reference frames. And here is just like a hack for solving problems with this. The hack is that more often than not, the math of these problems is going to be easiest for you if you make very careful choices about where to place these reference frames. Okay, so at the instant considered, which more often than not is what these problems are asking for, is they're asking you to analyze the movement at the instant shown. If at that instant shown, you put both frames with their origins at exactly the same location, you'll find that that's going to help you. So origins being coincident is going to make things nice. If you place the two frames so that corresponding axes are collinear, so collinear means that they actually lie on the same line. So if I put my little y on this same line as my big Y, that would be collinear. And then also if corresponding axes are parallel, this is going to be nicer as well. So the way that I drew it in the Frisbee golf example, I did very much on purpose, right? So I put the x direction on the little frame parallel with the x direction of the big frame. The y direction of the little frame is in the exact same direction or parallel to the big Y frame, and same with the Z frame. And I did that on purpose. Okay, so you'll get a handle for this as you do more problems. Okay? All right. So now we're going to talk about the equations that help us to write down the absolute velocity of the ant relative to the big XYZ frame. And then we're going to do the same thing for acceleration. So remember, we know something about the relative motion of the ant relative to the disk, but what we really want to know going forward is the absolute motion of the ant relative to the inertial reference frame. Okay, so here's our first equation. We're going to do like I always do and go variable by variable and define each of these variables. Okay, so VB on the left here, this is the absolute translational velocity of B. Or in other words, this is the motion of B as observed from the big X, big Y, big Z frame. Okay, so that's that wild and crazy motion that you see as the disc golfer. All right, VA is very similar. This is the absolute translational velocity of A, yada, yada, yada. Same as for B. Okay, omega here, I'm not sure why the book switches from a lowercase omega in the previous equations to an uppercase omega here, but they still represent the exact same thing. So this capital omega here is angular velocity. This is the angular velocity of the little x, little y, little z frame with respect to the big X, big Y, big Z frame. Okay, so essentially, this is the angular velocity of the Frisbee. Okay, we've seen this quantity before, RB/A, and it means the same thing as always. This is the position of B with respect to A, or the vector, going from A to B. Okay, and our last item here is VB/A, little x, little y, little z. This is probably the most confusing one, but it's kind of our new one for this equation. So this is the velocity of B relative to A as measured by an observer attached to the little x, little y, little z frame. Okay, so essentially, this is that forward-backwards velocity of the ant that we see when we are shrunk down to ant size and observing as we spin around with this disc. So it's the very simplified movement of the ant or the particle. Okay. All right, let's do the same thing for acceleration. Here's our acceleration equation. It's a little grosser than velocity, but we can manage. Okay, acceleration of B. This is the absolute translational acceleration of B. In other words, the motion of B as observed from the big X, Y, Z frame. Acceleration of A is the same, except with with A. A, B/A, little x, little y, little z. Very similar to V, B/A, little x, y, z. These are acceleration and velocity of B with respect to A as measured by an observer attached to the little XYZ frame. And finally, omega dot, very similar to omega. These are angular acceleration and velocity of the little x, little y, little z frame relative to the big X, Y, Z frame. Okie dokie. All right, let's try to make this more concrete with an example. Okay, so we're going to do an example. We have this kind of forked rod thing. This is all one rigid body. And this thing is spinning about the fixed point O here. Okay, so it's doing fixed axis rotation, spinning in this way. Okay, then we have this block that is within this forked rod, and it's being dragged in towards the center of the forked rod because it has this rope or this cord that's being pulled down through this fixed axis of rotation. Okay, so the block is being pulled in along the length of the forked rod in towards point O. So let's read the problem statement. It says block A, which is attached to a cord, moves along the slot of a horizontal forked rod. At the instant shown, the cord is pulled through the hole at O with an acceleration of 4 meters per second squared and a velocity of 2 meters per second. Determine the acceleration of the block at this instant. The rod rotates about O with a constant angular velocity of 4 radians per second. Okay, so it's asking about acceleration. And I have this problem where I have multiple rigid bodies, and I know some things about the forked rod, but I'm being asked about this separate rigid body A. So these two things are not on the same rigid body, and that's what clues me into using the equations from today. Okay, so I'm going to go grab this acceleration equation. Paste it down here. Okay, and I'm going to go variable by variable and try to find all of these variables. Okay, first off, let's double check that what it's asking me for is this A, B thing. Okay, so it says determine the acceleration of the block. Okay, well, we said that B is the ant. Well, in this problem, I think this block here is the ant. So, in fact, I'm actually going to cross out the letter here. I'm going to replace that with a B. Okay. So, the ant is moving relative to the frisbee. Well, what's the frisbee? Well, I think the frisbee is probably this forked rod, because this forked rod is a completely different rigid body, but B is moving on this forked rod, and this forked rod in and of itself is doing fixed axis rotation about O. So if I were you, I would put my little XYZ frame at the origin, and I would go little x, little y. Okay? And then lastly, I need to set my big unmoving frame. However, remember that piece of advice where I said it's going to be useful to you to set that frame as identically to your little frame as possible. Okay, and so for this problem, I have no reason not to put it at the same origin and in the same orientation as my little frame. So I'm going to do this. And as we fill out the equations here, you might see why this is a good choice, because certain things are going to go to 0. Notice also that I placed these frames smack on top of the fixed axis of rotation. I put them at O. And because I did that, because I made that choice, this term here is going to go to 0. Right? So A is the origin of my little XYZ frame, and this point doesn't translate at all because it's the fixed axis of rotation. This frame rotates with the forked rod, but it doesn't translate at all. Okay, so acceleration of A is 0. Okay, and then it says determine acceleration of the block at this instant. All right, now B is in fact the block. I made a good choice about my frames, so I'm going to say acceleration of A is 0. What is my angular acceleration? Well, it tells me that I have a constant angular velocity. And when angular velocity is constant, it means that alpha is 0. So in fact, this also goes to 0. So that whole term gets crossed out too. Now, what is omega? Omega is the angular velocity of the forked rod, or that little red frame. And I'm told that omega is going this direction at 4 radians per second. Well, if I do my right hand rule and I follow my fingers in the direction of that omega arrow, my thumb points out of the page in the direction of positive z. So omega here should be positive 4 k hat. Right, what is r b slash a? Well, that's the vector from A to B. So from A to B at the instant shown. And I see that that is 100 millimeters in the little I hat direction. And notice that this is given in millimeters, but everything else in the problem is in meters. So I'm going to go ahead and translate that into meters. So I believe this is 0.1 meters I hat. Little I hat. Okay, 2 more things that we need. V, B slash A, little x, y, z. Okay, so this is the way that B moves as measured by an observer who is fixed to this forked rod. Okay, well, it tells me that this cord is being pulled down through the hole at O with an acceleration of 4 meters per second squared and a velocity of 2 meters per second squared. Okay, so B is coming closer to that origin O at 2 meters per second purely in the little I hat direction. And acceleration, it tells me that cord is being pulled in towards O at 4 meters per second. Oh, sorry, I did this wrong. This is a negative I hat, right? Because it's going towards the origin, and this is a minus 4 I hat. Okay. The rest is just plugging these vectors into the equation and evaluating my cross products. So I'll do that for you as well. So acceleration of B equals, okay, this omega cross r. So I have 4k cross 4k cross 0.1 I plus 2 4k cross V, B slash A is minus 2I plus minus 4I. All right, so I see 3 cross products. Three cross products here, so 1, 2, and 3. I'll do 1, 2, and then 3. So 1 is I, J, K, 0, 0, 4, 0.1, 0, 0. I minus J plus K. All right, 0 minus 0. 0 minus 4 times 0.1, and then 0 minus 0. All right, so a negative and a negative. I think I have 0.4 j hat. All right, second cross product. I'll have I, J, K, 0, 0, 4, and then the resultant of that last cross product, which was 0.40. So minus J plus K. All right, we've got 0 minus 4 times 0.4. j is 0 minus 0, and 0 minus 0. Okay, so this is minus 1.6 I hat, and then the last cross product. 0, 0, 4, minus 2, 0, 0, I minus j plus k. 0 minus 0, 0 minus 4 times minus 2, and 0 minus 0. Okay, so I see 3 negatives, so minus 8j. All right, let's keep chugging along. So AB equals the result of this cross product here. So minus 1.6i plus 2 times this third cross product, so minus 8j, minus 4i. Okay, so this should be, let's see, acceleration of B equals minus 5.6i minus 16j meters per second squared. All right. Okay, that's everything I'm going to cover for today. All right, so I am doing several other examples of problems like this in the recitation that is dated 2/18/26. So if you want further practice with these, please go see the recitation video next. All right, thank you. Bye-bye.